We all use it every single day, right? You pull out your phone, open a map, and boom, there you are. But have you ever stopped to think about how it actually works? Well, that's what we're going to dive into.
Seriously, it feels like a little bit of magic. That little blue dot just knows. It knows when you turn a corner, when you're stuck in traffic. It follows your every move. It's not magic. It's this incredible symphony of physics and engineering. And today, we're going to pull back the curtain. Okay, so first things first, we got to get the name right. Most of us, myself included, just call it GPS. But that's kind of like calling all sodas Coke. GPS is actually just one piece of a much, much bigger puzzle. The real name of the game is GNSS. So yeah, GNSS. It stands for Global Navigation Satellite System. And you can think of it as the family name for all of these incredible systems. It's the whole technology that lets your phone or your car figure out where it is, down to just a few meters, by listening to these super faint signals from way out in space. And what's really wild is that it's doing so much more than just putting a dot on a 2D map. It's calculating your position in 3 dimensions, so latitude, longitude, and how high up you are. Plus, it knows how fast you're going, your velocity, and maybe most important of all, it gives us this ridiculously accurate time signal that's used to sync up everything from cell phone networks to financial markets. Now, this whole thing isn't just run by one country. It's this massive global effort. Think of it like a worldwide team where different countries and regions have all launched their own fleets of satellites, all working together to make sure that no matter where you are on the planet, you can get a signal. And here are the major players. You've got the one we all know, GPS from the USA, then there's Russia's GLONASS, Europe's Galileo system, and China's BeiDou. What's cool is your phone isn't just listening to one of these. It's probably listening to signals from a bunch of them all at the same time. That's how it gets a lock on your position so quickly and reliably. Okay, so we've got all these satellites whizzing around the Earth, broadcasting signals. But how do we get from that to you ordering a pizza to your exact location? Let's get into the nitty-gritty of how this whole system is built. You know, the easiest way to wrap your head around this is to break it down into 3 main parts. You've got the stuff in space, the stuff on the ground, and then, well, the stuff in your hand. First up, you have the space segment. This is pretty straightforward. It's the satellites themselves, the whole constellation orbiting thousands of kilometers above us. And you can think of each satellite as a ridiculously precise clock, just yelling the time and its exact location over and over again. Then you've got the control segment. This is the ground crew, the unsung heroes of the whole operation. It's a network of monitoring stations spread all across the globe. Their job is to constantly track the satellites, make sure they're in the perfect orbit, and keep their atomic clocks perfectly in sync. Without these guys, the whole system would fall apart pretty fast. And that brings us to the third part, the user segment. And that's you. Or more specifically, it's that little GNSS chip inside your phone, or your watch, or your car. Its only job is to be a really good listener, to pick up those signals from space and then do some pretty clever math. So, about that clever math, how does your phone take those signals and turn them into a pinpoint location on Earth? It all comes down to a really neat geometric trick. And that trick is called trilateration. Now, you might have heard of triangulation, which uses angles. This is different. Trilateration is all about measuring distance. If your phone can figure out how far away it is from a few different satellites, it can figure out exactly where it is. Okay, let's build this up. Imagine your phone picks up a signal from just one satellite. All it knows is its distance from that satellite. So you could be anywhere on the surface of this giant imaginary bubble in space, with the satellite at the very center. Not super helpful yet. But what happens when we add a second satellite? Well, now you have a second bubble. And where can you be? You have to be somewhere where those 2 bubbles intersect. And the intersection of 2 spheres is a perfect circle. See? We've gone from a whole sphere of possibilities down to a single circle. We're getting closer. Now for the third satellite. It creates a third bubble. And where does a sphere intersect with a circle? It hits it at just 2 possible points. We are so close now. Usually one of those points is a ridiculous answer, like it's moving at 10,000 miles an hour or it's deep inside the Earth. But to be absolutely sure, we need one more. And this is why that 4th satellite is the magic number. Its signal intersects with only one of those 2 points, confirming your exact location. But it does something else that's absolutely critical. It helps fix the time. See, your phone's clock is good, but it's not an atomic clock.
That fourth signal lets your phone sync its time perfectly with the satellites, which is what locks in that super precise 3D position.
Of course, in the real world, it's not that simple. That signal has a long journey from space. It gets bent and delayed as it travels through our atmosphere. And if you're in a city, the signal can bounce off buildings before it gets to you. That's called multipath error. There are also tiny clock errors to account for. Even the position of the satellites in the sky matters. If they're all bunched up together, your accuracy goes down. You want them nice and spread out. So your phone can get you down to a few meters, which is amazing. But what if you need more? What if you're a surveyor building a bridge or a scientist measuring the movement of continents? For that, you need to level up to some seriously high-precision techniques. We're talking centimeters or even millimeters.
And this really shows the trade-off. For the absolute best, millimeter-level accuracy, scientists use a method called static surveying. They literally leave a receiver in one spot for hours, just soaking up data. But for construction or engineering, you can't wait that long. So they use something called RTK, which uses a second, fixed receiver as a reference point to send real-time corrections. It gets you centimeter-level accuracy in just a couple of minutes. Pretty incredible. When you step back and look at the big picture, you realize GNSS has become this silent, invisible utility that we all depend on, just like electricity or the internet. It's truly a foundational technology for our modern world, running in the background of everything from shipping and farming to your daily commute. So that leaves us with one last mind-bending question to chew on. Now that we know how this all works, what's next? What happens when this technology gets even better, even more precise? What kind of future can we build in a world where every single object, from self-driving cars to tiny delivery drones, knows its exact location on the planet, down to the centimeter? The possibilities are just staggering to think about.